Hello dear students, welcome to the first laboratory work, which is called the physical meaning of the derivative, the concept of differential, tangential and normal acceleration. Let's talk about the physical meaning of the derivative. Let's ask about velocity. Let a material point move in a straight line, and let s is equal s of t be the path traveled by the point during time, t from the beginning of the movement. In a time interval from t to t plus delta t, the point will pass the path s of t plus delta t minus s of t. So, this way the average velocity for this time interval is equal to vector v. And in the slide you can find the shown equation. If the motion is not uniform, then vector v at a fixed t, it will change with the change in delta t and the smaller delta t. The better it will characterize the motion of the point at time t. The velocity of a point at time, instantaneous velocity, is the limit to which the average velocity tends when delta t tends to 0. So it means the velocity v at time t is determined by the equality, which you can see in the presentation slide. Thus, the velocity of motion at time t is the limit of the ratio of the path increment s of t plus delta t minus s of t over the time interval from t to t plus delta t to the time increment delta t, when delta t tends to 0. For example, if a material point moves according to a law s is equal to gt squared divided 2, the law of free fall, then vector v is equal to the followed equation. In the same way, if we repeat the above reasoning, we can come to the concept of instantaneous acceleration. You can find an equation of instantaneous acceleration in the slide. Please check it out. So the second derivative has the physical meaning of acceleration. And let's go next and talk about differential of the function. The differential of a function is the product of the derivative of the function and the increment or differential of the argument. If the function y is equal function of x is differentiable at x0, then the differential and the derivative are related by the equality. dy is equal to the followed equation in the slide. The analytical meaning of the differential is that the differential dy is the main part of the increment of the function. For small increments, dy can be considered as delta y. From the meaning of the differential, its important practical significance follows. Finding the differential of a function allows you to determine how much the function has changed if there have been small changes in the variable on which it depends. And there is an example. There is a cube with edge length L is equal to 1 meter. How much will the volume of the cube change if the edge length has increased by delta L is equal to 1 centimeter? Given that the increment of the volume of a cube function with small changes in the length of its edge argument is approximately equal to the volume differential we get. And delta V is equal to the followed equations. Let's go next and talk about the first point. Let us consider the mechanical meaning of the differential of a function. Let s is equal function of t be the distance of a point moving in a straight line from the initial position. T is the time travel. T is the travel time, by the way. The increment delta s is the path traveled by a point in a time interval delta t. Then the differential will be ds is equal differential function of t delta t. This is the path that the point would have traveled in the same time. Delta t, if it had maintained the velocity function of t achieved by time t. For an infinitesimal delta t, the imaginary path ds differs from the true delta s by an infinitesimal higher order relative to delta t. If the velocity is not zero at time t, then ds gives an approximate value of the small displacement of the point. Thus, from the point of view of mechanics, such a substitution means that we consider the moment on the considered section to be uniform. And the next point. Let Q be equal to Q of T is the amount of electricity falling through the cross-section of the conductor, T is the time, and delta T is that certain period of time. Delta Q is equal to Q of T plus delta T minus Q of T is the amount of electricity falling through the specified cross-section for the time interval from moment T to moment T plus delta T. Then delta Q divided delta T, it's called the average current for the time interval. Delta T and is denoted I average, and the limit I average is equal to the followed equation. This is the current strength at a given time, instantaneous current strength. The differential dQ is equal to I delta T is equal to amount of electricity flowing through the cross-section of the conductor during the interval delta T, if the current strength will be constant and equal to the current strength at time t. The next point, the third point. Let us give an inhomogeneous rod. A rod is called homogeneous if any two sections of it of the same length have the same mass, and inhomogeneous otherwise of length e, and let m be equal to m of x be the mass of a rod of length x. 0 is smaller or equal to x, which is smaller or equal e, measured from a fixed end. And you can find a picture on the slide. Then delta m is equal to m of x plus delta x minus m of x is the mass or the part of the rod bounded by the points located at a distance x and x plus delta x from the specified end respectively. Density. The value average density is equal to delta m divided delta x is the average linear density of the rod in the specified area. Then the linear density is equal to limit average density delta x tends to 0. If the density is constant, then the rod is uniform. For an arbitrary, generally speaking, inhomogeneous rod, the differential dm is equal density delta x is equal to the mass of homogeneous rod of length delta x with the constant density, equal to the density of the rod under consideration at a given point. And the next part that we are going to talk about, called normal and tangential acceleration. In any case of movement, the speed is a variable value. Consider acceleration is equal to dv over dt is equal to the second derivative of s. This is also a vector quantity. When moving in the covered direction vector v, it also changes in direction. Which way, at what velocity? Expression 1 doesn't answer the equations. And please look at the followed figure in the slide. We introduce a unit vector tau associated with point A and directed tangentially to the trajectory of the point A. Vectors tau and v at the point A match. Then you can write the shown formula. And then find the acceleration. A vector is equal to dv over dt, and it's equal to tau vector dv over dt plus v d tau vector over dt. And all of this is equal to a vector tau plus a vector n. We get two terms of acceleration. A vector tau is the tangential acceleration coinciding with the direction v vector at a given point, and vector an is the normal acceleration, or centripetal, since it's directed to the center of curvature, perpendicular to the vector tau. Tangential acceleration is determined by the formula in the slide, where dv over dt is the rate of change of the velocity vector v magnitude. Acceleration a vector tau characterizes the change in the velocity vector by value. If dv/dt is greater than 0, then vector a tau is directed in the same direction as the vector v, so it means acceleration motion. If dv/dt is smaller than 0, then vector a tau is directed in the opposite direction v vector. So this is the slow motion. If dv/dt is equal to 0, then vector a tau and vector v are constant values. So these are motion with a constant modular velocity. Let's go to the next part and talk about normal acceleration. The formula a vector n is equal to v d tau vector over dt. The rate of change in the direction of the tangent to the trajectory d tau over dt is determined by the speed of movement of the point along the circle and the degree of curvature of the trajectories. The degree of curvature of a plane curve is characterized by curvature c. Radius of curvature r is the radius of a circle that merges with the curve at a given point on its infinitesimal section ds. R is equal to 1 over c is equal to the following equation. The centers of such circles are the centers of curvature of points O and O prime. And please look at the third figure. The rate of the tangent direction change can be expressed as the product of the rate of change of the angle by the unit vector, showing the direction of change of the angle. d tau over dt is equal to d phi over dt n vector, where vector n is a unit vector directed perpendicular to the tangent tau at a given point. So it means along the radius of curvature to the center of curvature. It follows from the third equation that d phi is equal to ds over r, but since ds is equal to v dt, then d phi over dt is equal v over r, and hence d tau over dt is equal to vr n vector. Finally, v d tau over dt is equal v squared over d over r n vector. So it means the shown formula you can see in the presentation slide. Normal acceleration shows the rate of change in the direction of the velocity vector. The magnitude of normal acceleration is v squared over r. The term centripetal acceleration is used when motion occurs in a circle. If the motion follows an arbitrary curve, then the corresponding analog is the term normal acceleration, perpendicular to the tangent at any point of the trajectory. So, returning to expression 2, we can write that the total acceleration vector for movement a point along the plane curve is a vector is equal to a vector tau plus a vector n. And you can find the fourth figure in the slide. It shows the relative position of the acceleration vectors. As can be seen from this figure, the total acceleration modulus is square root from a squared tau plus a squared n. Let's consider a few limited special cases. The first one is about when uniform rectilinear movement. The second is when equidistant rectilinear motion. And the last one is when uniform movement around the circle. So, in the laboratory work 1, we considered the physical meaning of the derivative, the concept of differential, tangential and normal acceleration. That's all for today. Thank you for your attention.